And what you need to do, this is to align the exhaust with the outwash you have. And if you change the fuselage, this angle will change. And so you need to change the exit, the exhaust nozzle, depending on the fuselage you have. Where are you compared to the fuselage, the distance, the type of wing, the size of the fuselage, the diameter, and things like that. And so that's why they are changing the exhaust nozzle depending on the type of aircraft on which you are mounting the engine. And so when you are doing a test on a test cell, so you do it with m dot bleed that is equal to 0. You do it with P bleed, the electrical power. I mean here everything related with the aircraft. 0. You test it with a bell mouse with, let's say, small corrections, a RAM recovery of 1, and you test it with a standard or reference nozzle. When you go to an aircraft, when the engine is mounted on an aircraft, the aircraft will take some m dot out of the compressor, will take some electrical power out of the shaft of the engine, will have a RAM recovery that is not equal to 1, and will have an exhaust nozzle that is not the standard or reference one. And you need to correct all that. And you need to have, for each of these factors, this one, this one, this one, this one, the change in thrust due to this parameter, the change in TSFC due to this parameter. At each value, let's say, of this quadruplet. So this installation manual, this installations effect, this is a huge document, of course, because there are so many factors changing in all directions. But I will show you in the PowerPoint presentation, in the, let's say, more Teams presentation, I will explain you with the numbers exactly what I mean by that. But this is the philosophy. And so, installation manual, installation effects, plus this CD spillage in the wind tunnel for the baseline value of the capture area ratio, plus the delta CD spillage on another experimental setup for the other values of the capture area ratio than the baseline, all this, you put here a correction number 1. When I say number 1, there are in fact few corrections there, because there is one here, there is one there, there is also one here and a second one there. So in fact, we should say here that we have 4 corrections, and here there is a correction 2. In fact, there are also 4 corrections, because you see that we have m dot electrical power, RAM recovery, and the exhaust nozzle. So 4 plus 4, 2, 4, and 4, 8 corrections. You have normally everything to define the aircraft performance. This is a very dangerous operation. You see, 8 corrections, 8 corrections, some of them depending on 4 parameters, plus a 5th one, which is very often the geometry. It is a rather dangerous operation. Of course, the manufacturers, the aircraft manufacturers for military aircraft or for civil aircraft, they are used to do that. If you try to do that alone, I'm sure you will fail, because it's not an easy problem, but they are used to do that, and normally it's done adequately. But there is a famous example, the famous example where, in fact, it has been a very difficult operation. The first one is the Concorde. For the Concorde, for the Mach number 2.02 in cruise, it was an extremely challenging situation to make this exercise. But they succeeded at the end. The Concorde was able to fly to the destinations he had at the beginning: Paris, Rio, London, Chicago, London, Washington, Paris, New York, and things like that. So for the Concorde, it has been a challenge, but it has been successful at the end. But the other one this is the MD-11. The MD-11 is the last big airplane that has been developed by McDonnell Douglas. And during the development of this aircraft, it's hard to understand exactly what happened, but there has been a succession of small mistakes. One of them has been clearly identified at the level of the lip suction thrust and the additive drag, mainly the lip suction thrust, And in fact, the MD-11, it's of course a matter of circumstances, had as a first customer a very challenging mission. It was Singapore Airlines flying from Singapore to Europe, Rome particularly, and due to mistakes, a succession of mistakes in this, and also don't forget something that I have mentioned in the past, but that is included somewhere in the problem, which is the decoil. Don't forget the decoil that is included in this drag. The decoil is included here, but it's something that is also coming from estimates. They were not successful in reaching the place they had to land. And of course, they made improvements, changes, but it was too late because they were failing with their first customer. And of course, at that time, so the problems are, let's say, making a kind of snowball effect. Some customers are, let's say, leaving the boat. You have less money to solve the problem, and even if you solve the problem, you are in a very difficult situation, and it led to the fact that McDonnell Douglas had to abandon the transport aircraft market and has been bought by Boeing. So, huge company. It was the second largest civil transport aircraft manufacturer in the US, huge company, let's say as huge as Airbus, almost, and they made a mistake in the definition of this aircraft, and that they could not solve on time, and they could not detect the problem enough, let's say in advance, and so it led to a problem. So it's a very difficult problem, but very important, and this problem is called the thrust drag bookkeeping. Thrust drag bookkeeping, because you see, it's always a problem of counting everything you need in thrust. We see, for example, that m dot is making that the thrust is decreasing, this makes that the thrust is decreasing, this makes that the thrust is decreasing, this makes that the thrust is decreasing. So the thrust is not what you have defined first. There are factors making to the thrust is 0.1% lower, 0.2% lower, 0.3% lower, and so you count, tack, 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 and at the end you have a lower thrust than expected. And it's also a drag problem because there are so many drag terms for the boat tail and for the intake that you can make very quickly an error in this computation. And of course, if errors are, let's say, compensating, it's okay. Or if you discover an error. But you see that the problem is so touchy, very difficult to find the right values and to do all this testing, that this problem can be certainly considered as a very important step in the preliminary design of an aircraft. You are doing this, it's preliminary design and not conceptual design, because you are already doing some, let's say, experimental things, like here. But it's very critical situation that makes that the aircraft could not satisfy the needs of the customer due to this thrust drag bookkeeping. So you need all terms related to thrust that are, let's say, positive forces, all forces related to drag that are negative forces, and this is the balance between these two that must be correct. If you make a mistake in the thrust part, or if you make also a mistake in the drag part, that could lead to a catastrophic situation, making that the performance of the final aircraft are not what you intended to have, due to this very complex situation of all these small forces and these small effects that are extremely difficult to understand, and that are very difficult mainly to quantify. And this is what you need to have. You need to quantify everything. Again, I will explain you with real values, with examples of the installation manual and examples of such a scenario, such a, let's say, logical, let's say, computation and understanding of the problem, how the problem is really solved by an aircraft manufacturer. But at least you have here the global explanation, and I have also defined at the adequate place in the course what we call the bell mouse, which is this ideal intake that you have when starting the engine, so, and that they will install on a test cell when they are testing the engine in takeoff, or let's say starting or taxiing conditions. Okay? So this is ending the part on the intakes. So internal flow we have studied, external flow we have studied, and it led to this spillage drag. And after that, this stress drag bookkeeping that is very important at the level of the preliminary design of an aircraft after the conceptual design. And I have also had then the opportunity to speak about installation losses, installation manual, installation effects that are extremely important. And that's why, if you remember well, in some performance curves that we have seen for the different engines we have discussed before, you have seen in the PowerPoint presentations for the turbojet, the turbofan, the turboprop, and so on. They are always giving the, let's say, conditions in which the the engine performance have been found, have been established, have been computed, or have been measured. And they say always sea level, they give a temperature, very often ISA temperature, 15 degrees Celsius. They give ram recovery is equal to 1. They have also very often a word related to the exhaust nozzle, and they speak about no installation, because there is m dot equal to 0 and P electrical also equal to 0. If you look to all performance curves that we have seen for turbojet, turbofan, after burning, turboprop, and I don't know what, always they indicate very clearly that they speak about non-installed performance, non-installed performance. And after that, you need to make all these corrections. Thank you.